Good morning, everyone. So first of all, there are cookies, and please don't give me leftovers because we should finish them before the end of the term. The other thing is, well, last time we started talking about sensitivity analysis, and we'll continue doing this time. I promise that I will post some kind of mock midterm during this week. I hope today or tomorrow. I can't be sure about this today or tomorrow because I have to get an answer from the other instructor. We are choosing kind of from a pool of questions the questions for the midterm, and the rest will go to the mock midterm. So I'll need to coordinate this. Okay, so back to sensitivity analysis. We talked about the main ingredient of sensitivity analysis, and this was the option, the tool that allows you to go from one basis, a problem with one basis, to a problem with a different basis. And if you recall, the formulas were like this. You separate the variables to two parts, basic and non-basic. So you want to maximize Z, which is the linear combination of basic variables and non-basic variables, under the conditions that some vector of coefficients, right-hand side, is equal to some matrix, the basis matrix times the basic variables plus the non-basic matrix times non-basic variables. And we thought that, oh yes, and of course this is equivalent to such a system, where you make xd actual basic variables. So the system is just multiply everything by b inverse. And here you get z is cn minus cd b inverse n x n. So make z a linear combination only of the non-basic variables, the basic variables coefficient 0, and this is the coefficients. These are the coefficients. This is z minus some number. Which is CDB. So this was our way to go from one basis to another basis. And last time we also talked about how it looks in an actual tableau. So if the initial problem has a tableau like this, some kind of table, we will find the vector of right-hand side on the right-hand side, the coefficient matrix somewhere here, so the columns of B and M somehow intermixed in this place. Here you have Z, here you have this vector C. And of course, in the initial problem, we have the place to stack variables. So here you have the identity matrix, and here there will be some numbers. And as you move to the part where SB is actually basic, you will find yourself with the following table. In the right-hand side, you will have the two right-hand sides, B inverse B. Instead of identity matrix, so basically you multiply this matrix of coefficients by B inverse, Instead of identity matrix, you'll find B inverse. Somewhere on the place where the basic columns are, you'll find columns of the form zeros, 1, and zeros again. Here will be z minus some number. These coefficients will be given by this formula. Maybe let me use these things to say to write it as follows. If you find yourself with a column in the initial table which is n, and here you have c of n xi, and here you have c xi. So the coefficients of some variable xi are given by such a column, and the coefficient in z is given by this number. Then the corresponding column here will be as follows. This will be, of course, b inverse nxi, and this number will be cxi minus cb b inverse nxi. So you have a way to find every coefficient in this last row just by using this number, this column, the vectors cb, which is somewhere here, and b inverse. This big n and this small. So this is all our knowledge about how to go from the initial matrix to the matrix with a given basis. Well, basically I summarized everything that we know. We know these formulas on the top, and we know how it looks on the table level. So maybe before I go on to sensitivity analysis, maybe any questions about this? This material that we discussed last time and the one before this, but maybe reading this way it might look a little different. I didn't write the previous time the actual tables. So maybe any questions about this? Okay, and now we'll talk about sensitivity analysis, which is basically about the following thing. If you make changes to the original table, to the initial problem, what will happen to the optimal answer? Well, what will happen if this table used to be the optimal table, which means all the coefficients in the last row are negative, and all the numbers on the right hand side are positive, which means it's optimal and feasible. The question is, what will be the new optimal table? And this way of getting from the initial table to a table with a given basis is, of course, very helpful. So let's look at some examples, and we'll discuss several classes of changes. So in this table you can change coefficients at different places, and they tend to have different kind of influence on the final table. For instance, you can change the coefficients in the last row, the cost c. You can change the right hand sides. You can change numbers in this matrix, coefficients in the constraints. So you can change all these numbers, and different changes lead to different kind of, they propagate to the final answer in different manners. So we'll discuss those separately. So our main example for today will be the following problem. Original table is has two constraints, the coefficients 2, 3, 5, 1, 0, 9, 1, 2, 3, 0, 1, 5, and z is 3, 4, 8, 0, 0. So of course, you can translate this table to the original problem. Here it's obvious that x4 and x5 are the stack variables, and the constraints are 2x1 plus 3x2 plus 5x3 equals 9. Similarly for second one, z is 3x1 plus 4x2 plus 8x3. All xi's, all the variables are positive. The question is find the optimal solution. And suppose you worked hard and you found that optimal solution or final table is like this: 1 minus 1, 0, 3, minus 5, 2, 0, 1, 1, minus 1, 2, 1, 0, minus 1, 0, minus 1, minus 1, z minus 14. So here, obviously x1 and x3 are are basic. The coefficients in the expression for z for these variables are 0. The columns are 1, 0, and 0, 1. So these are the basic variables. This solution is obviously, well, if only it is equivalent to this one, it's obvious that it is optimal. It is feasible, these numbers are positive, and it is optimal because degree z, all these coefficients are negative. So this part is given to you. You know that the final table, once you apply the simplex method to this problem, the final table is like this. And now the question is, without performing, well, too many calculations, answer the following questions. So maybe let me leave some space here. I'll put some extra information and I'll formulate the questions here. So first class of changes will be change in coefficients in non-basic column. So change of coefficients of some non-basic value. And the question is like this: if coefficient of x2 in z changes to 7, and the coefficient of x2 in equation 2 changes to 3, what is the new optimal solution? So the problem is, in the original problem, some of the coefficients turned out to be wrong. Maybe they came from some estimates of the costs, of the amount of resources needed for production. And now it turns out that, well, we started the production, the amount of resources is different. Instead of, so in the second equation, the coefficient of x2 now is 3. It used to be 2, but now it turns out the correct one is 3. And also, the profit, well, the or cost or whatever, the C coefficient of x2 changes to 7. So this number used to be 4, now it becomes 7. So the changes will be here and here, all in the column of x2. And the question is, now, find the new optimal solution. Okay, so the idea is to start with this solution, and here we have x1 and x3 are basic. So the first idea is, well, the changes are not huge. We only changed one column. So maybe if we still keep x1 and x3 basic, we will get the optimal solution for the new problem as well. So we have to check this, of course. So we have to find the final table which corresponds to the new problem and the same basis, x1, x3. So let's find out, well, of course we'll use these formulas for such kind of tricks. Let's find out what is the basis matrix, what is its inverse, and so on and so on. So let's try to employ these formulas. So first question, what is the basis matrix? What is the matrix B?
2, 1, 5, 3.
2, 1, 5, 3. Yes. So my matrix B consists of the columns of the original matrix which correspond to the basic variables, which are x1 and x3 in this case. So B is 2, 1, 5, 3. We know we always need not quite B, we need its inverse. What is the inverse of B? That you don't even have to remember the formula for inverse of 2 by 2 matrix. You can just read it off some of the numbers which are already written here. So where should I look? Yes, x4 and x5. To go from this matrix to this matrix, I have to multiply by the inverse. So if I multiply this identity matrix by the inverse, I get this matrix. So this must be the inverse. That's the information available there. So the inverse is already given to me. 3 minus 5 minus 1, 2. Okay. Now let's think about how the changes will propagate to the new final table. So my changes are in these numbers. This number and this number. What parts of the final table will change and what won't? So what numbers I expect to become different? For this we'll have to look at this picture. So what will be different? Will be changed? Well, of course no. We changed coefficients of non-basic variables. So we didn't change the columns of basic variables, so this matrix does not change. Small b, once again, doesn't change. 9,5, as it used to be, still it's 9,5. So the vector of right hand side is not going to change. The vector of coefficients. Okay, so here I have coefficient of xi minus cb, the inverse nxi. What changes? cb does not change. I did not change these things. 3 and 8 are still the same thing. So maybe I can write it cb in both problems and cb. B inverse didn't change. This thing, cxi and nxi. In most columns, it does not change once again. So if the column itself does not change, say the column of x4 used to be 1, 0, and the coefficient was 0, still it is 1, 0, coefficient is 0, and these are the only numbers which we will employ to find out whether this coefficient in the last row here. Because this minus 1 is exactly 0 minus CBB inverse times 1, 0. The only change the only place which can change is, well, right here. So these things might change. Why? Well, this coefficient actually did change. This column actually did change. And the same goes for the computation of B inverse NXI. The column changed, so there might be some new numbers over here. So the only change is right here.
So that formula is CXI minus CB, the inverse. That gives you the whole column or just the top?
So this thing is just a number. This
Oh.
number. In this case, it would be minus.
So we won't be able to calculate
The column, it's over there. B inverse
Oh,
times the
okay,
column.
right.
So to go from here to here, you just multiply this whole matrix by B inverse. So each column gets multiplied by B inverse. And these numbers, well, you'll have to do something different. You take these numbers, and then you subtract some linear combination of these rows, and this linear combination turns out to be CB inverse. Okay, so if x1, x3 are kept basic, the only change in the final tableau, in the tableau will be in column of x2. So it turns out that if you change the coefficients of the non-basic variables, the only changes to the final tableau, well, not the final table, but the table where the same variables are kept basic, are in the same column. So new column for x2 is like this. So my new column, original column, is now not 3, 2, but 3, 4. So my updated final column is B inverse times this updated column. B inverse times updated column. I have the B inverse, 3 minus 5 minus 1, 2. Updated column is 3, 4. So it's 9 minus 20 minus 11 minus 3 plus 8, 5. Oh, sorry. It's updated not to 4 but rather to 3. So this thing is 3. So let's calculate it once again. 9 minus 15 minus 6 minus 3 plus 6 plus 3. So what did we compute right here? We computed this new column. Instead of minus 1, 1, we will now have minus 6, 3. Actually, I performed kind of calculation which I didn't have to apply. To be honest, I wanted first just to check whether the new solution will be optimal. I mean, I know it will be feasible, these numbers did not change. Actually, it will be the same solution. x1 is equal to 2, x3 equal to 1, all the other variables are 0. The only question is it optimal. To check this, I only have to check whether this number is negative. So basically, I'll have to update just this number. So I can do this. My new coefficient of x2 is not 4, it got updated to 7. So what I want to compute is my new coefficient of x2 minus CB, the inverse, a new column of x2. This number is what will be here. Okay, let's compute it. Cx2 is 7. CB, actually, there is a funny thing. This CBB inverse can also be found among these numbers. It's something that we didn't discuss, but maybe it's a good trick. I mean, of course, CB is easy to find, it's 3, 8, and B inverse is written, but there is a trick. This whole answer, CB times B inverse, is also written somewhere. Can anyone think about how to find this CB B inverse?
Use one of the non-zero numbers on the last row.
On the last row, we had these numbers. So if you look at this thing, at this formula, and you try to compute what happens at these places, you'll find out that what you do is you take, right here you have a vector of zeros, so these are the coefficients of zeros, minus CB the inverse times the identity matrix. So it is in fact minus CB the inverse. So in this place you'll find minus CB the inverse. And also useful to know these particular numbers because, well, these coefficients, the coefficients of the set variables in the final tableau, are actually the shadow prices of the equations. So, well, negative the shadow prices of the equations. So in fact, the vector CB the inverse is the vector of shadow prices of the equations. And it can be found in this row. Okay, so minus CB the inverse. So CB the inverse is vector 1, 1 times the new column, new updated column is 2, so 3. So it's 7 minus 6, 1. So what should I understand about this 1? I just want to know whether it's positive or negative. If it is negative, then I have no problem. Then my new solution is still optimal. Unfortunately, this 1 is positive. So my new solution is not optimal. Okay, so let me say that new tableau is, I'll just copy the old one, except I plug in all the numbers, all the new numbers which I computed. Minus 6, 3, 1, and the rest is the same. 0, 3, minus 5, 2, 1, 2, minus 1, 1, 0, minus 1, minus 1, 7, minus 0. So unfortunately, I did not find the optimal solution. This solution using 2, 1 for x1 and x3 is not optimal. I can increase x2 to make z even larger. So what should I do to find the optimal solution? Yes, of course. I can increase x2 to make that larger, so let's do it. Let's perform simplex algorithm on this solution. It is, after all, a basic solution. x1 and x3 are basic variables. Well, x2 is not basic, but can be increased. So let it enter the basis. Some of the variables will have to leave. Which one will leave? Well, here the quotient is negative. Here it is 1/3 positive. So this is the smallest positive quotient. So this will be my pivot row. And next I'll just perform the simplex operation. From this tableau, I'll go to, okay, so let me not repeat this mistake. Let me first compute this row to find out whether I get an optimal solution. So I'll subtract 1/3 of the second row from the last one. 0, 0, minus 1/3, minus 1, minus 1/3, so it's minus 2/3, minus 1, minus 2/3, so it's minus 5/3, and z minus 14 minus 1/3, so it's minus 14 and 1/3. here I'll get 0, 1 there, and then some. Actually, it doesn't matter. So it matters somewhat. This number is important, this one there, and this number. So here I'll take the first row and add 2 times the second one, so it will be 2 plus 2 times 1, 4. All other numbers are not important. Why they are not important? Well, I see that I found the optimal solution. All these numbers are negative. I find what is the actual solution. x1 is 4, x2 is 1/3. And well, the value of my function, the new optimal value is 14 1/3. So this is optimal. x1 is 4, x2 is 1/3. Okay, so now we found the new optimal solution. So at this point I want to emphasize that sensitivity analysis always works basically the same way. What you do is you have some changes in the original formulation of the problem. Well, you use these formulas to find out how they propagate to the final term. So they'll discuss several cases. But for instance, if the changes in the coefficients of non-basic variables, the propagation will be only in the same column. Okay, so we find out how it propagates to the final table. You'll get some basic solution. Well, sometimes it will be not optimal. Well, re-optimize it. If it's not optimal, perform several steps of simplex algorithm to make it optimal. Sometimes it will be not feasible. So we'll talk next time, if you get a non-feasible solution, how to get back to a feasible solution. It will be a slightly different simplex algorithm called dual simplex algorithm. But still, there is a way to go from a solution which is close to the optimal, but not feasible, to the actual optimal feasible solution. And in some real annoying cases, you'll get a solution which is both not feasible and, well, not optimal in the sense that these coefficients are not all negative. Then you have to do a certain combination of them. The simplex algorithm and some other kind of algorithm to find a new optimal solution. But still, it's always possible to go from a basic solution which is not far from optimal, or might be not feasible, might be not optimal, but it should be kind of not too far from optimal, to the actual optimal solution by doing not so many steps of some simple algorithm, like the simplex algorithm, and next time we'll discuss the dual simplex algorithm. Okay, so maybe any questions about this change? So let me summarize. This. Let me summarize what happened. Non-basic variables. Change. And I mean only these coefficients change. You choose some number of columns and you change only those columns. Then, well, first of all, the new solution, with the same basis. Is the same. So if it used to be 2,1 for x1 and x3, then it is still 2,1 for x1 and x3. In particular, so still feasible, but might be not optimal. How to check whether it's not optimal or whether it's optimal? It is optimal exactly when the new coefficient of xi, cxi minus cbb inverse and xi is negative. So 0. So if the updated coefficients in the last row are all negative, well, the same solution is still optimal, still the answer. If it is not, so if it is not basic, not optimal, make xi enter the basis. Basically perform single subgroup. So if one of these coefficients is actually positive, then you can make it enter the basis, increase the objective function, so actually do this, perform single subgroup. Maybe some new insight, so remark. We just said that this vector, CBB inverse, which appears so prominently here, we said that it is actually the vector of, well, minus e is the vector of coefficients of the set variables, and we also know that the coefficients of the set variables in the primal are the values of the decision variables in the dual. So these numbers appearing in this vector are actually the shadow prices of the equations. So this is the vector of shadow prices. So in fact, if you want to find the shadow prices, it is in fact CBB inverse. In particular, what is this thing? C xi minus CBB inverse. Let me say y times m xi. This y in CBB inverse. Y is the vector of shadow prices. So if you take the original cost and subtract the linear combination of these numbers with these coefficients, well, what do they say? So these numbers is how much resources of different types the production of the vector nxi, 3, 2 in this case, will be the production of 1 unit of x2 consumes 3 units of resource corresponding to equation 1, 2 units of resource corresponding to equation 5. So if you multiply 3 by shadow price of resource 1 plus 2 times shadow price of resource 2, this will be the total cost of resources consumed in production of 1 unit of X2. Well, and now you take the profit that you extract from sale of X2, or in this case, and subtract this thing. So this is precisely the reduced cost. Is the reduced cost the total profit from the sale of 1 unit of X2 minus the cost of resources which I used to produce X2. So the revenue which, well, yeah. And of course we know that it should have been the reduced cost. It is the coefficient in the corresponding column right here, so it must be the value of the dual slack variable, which is the reduced cost. And what is this equation telling you? Well, if the reduced cost is negative, you should not produce such. You should not continue producing. You should not start producing this particular product. If you can make some profit out of production, well, do this. So this whole thing actually has some economic interpretation as well. So any questions about updating that one code? Think about a different kind of change. Introduction of a new variable. So you have some production problem, you would produce 3 products, chairs, tables, and doors, and now you want to introduce a new line of production, I don't know, window panes. And you know that it will consume some resources, so you introduce, instead of three variables, 3 decision variables, x1, x2, x3, you introduce a new one, in this case 6, with some coefficients, some profit. So you add one flow column to the original problem. And the question is, well, as usual, how will it influence the optimal solution? So if you introduce a new line of production, should you actually use this line of production? And if so, well, how busy should you be using this line of production? So the example here will be what happens if we add a column added to the original problem. So you introduce a new variable x6, and now your problem becomes exactly what it used to be, but now imagine here I squeeze the column x6, 2, 3, 4. What will be the new optimal production? Well, it looks like it's somewhat different from the previous kind of problem that we considered. It looks like it's not that we change some coefficients, we actually add some new variable. But to be honest, it's exactly the same. How is it exactly the same? Well, we can think that the original problem did have this variable x6. It's just all the coefficients used to be 0, so we didn't bother writing them. But now we change these coefficients 0, 0, 0 to new coefficients 2, 3, 4. So we should employ exactly the same thought process. We are changing coefficients of one variable, which is obviously non-basic, and well, same kind of thought process. The change will propagate only in one place, only in the column of x6. So we'll find what is the coefficient of x6 in the final table. If it is negative, we are done, which means x6 should remain non-basic and the x6 should be actually 0. If it is positive, well, we should introduce x6 as part of basis, perform a couple of steps of simplex algorithm, and find the new basis, new optimal solution. So, let's do this. So we'll think about this as changing the coefficients of x6 from 0, 0, 0, from such column to 2, 3, 4. So from this column, we'll update it to this column, and then we'll employ the same process. So my new column corresponding to x6 is 2, 3, column of coefficients in the equations, in the constraints. My new cost for x6 is 4. My shadow prices y1, c, y1/3, which is cb inverse. Did not change, still 1, 1. So my new reduced cost, which is cx6 minus cb inverse and x6, will be 2, 3, 4 minus 1, 1 times 2, 3. So it is minus 1. It is negative. So my new table will be exactly what it used to be. It is 2, 1, 0, minus 14, 0, minus 1, 0, minus 1, minus 1. And for x6, I'll have an extra minus 1. So this will be the new column for x6. And since all the coefficients are negative, the previous one are negative, because this was the optimal solution. The new one, well, turns out to be negative. Didn't have to be, but turned out to be negative. So the optimal solution is x1 is 2, x1 is 1, x2, x4, x5, x6 are all equal to 0. In other words, if the reduced cost for x6 is negative, it means there is, I cannot extract extra profit from introduction or production of this product x6. So I should not actually produce it. And once again, if it turned out to be positive, I would just make this column a pivot column. I will actually compute these numbers to find out which one is a pivot row and perform the simplex algorithm. Most likely just 1 or 2 steps. So this problem is not at all different from the very first one. It is, in fact, same thing, changing the coefficients of a variable which is not basic. It's just that here we didn't see this variable, we didn't even think about it, but still the same thinking can be applied. So maybe any questions about this kind of analysis? Okay, so now we know what to do if we have, well, one thing, introduction of new production line, this kind of change, another thing, a mistaken estimate of what amount of resources were consumed by production of one old product, or maybe the profit from sale of this old product, but only when this product was non-basic, which means when we actually did not produce this product to start with in the optimal solution. But sometimes you do find out that you made some change to, no, you find out that something in the formulation of original problem was different about a product which you do produce. Actually, that's what happens even more frequently. I mean, you start producing something and you find out that, well, something was wrong. I mean, the number of steel used to produce it was not 5 kilograms, but 7 kilograms. The profit turned out to be not optimistic $8, but pessimistic $5, something like this. So let's discuss this kind of change. So third kind of change will be change in coefficients of a basic variable. So let's look at what happens if we change some coefficients, but now a basic variable. What changes will get? Unfortunately, they will not be localized as I used to say. If you change coefficients of the basic variable, of a basic variable, B will actually change. It will have one new column. If you have one column which changes in B, in the inverse, you have basically change everywhere. Similarly, CB will change, so this vector will change. This whole thing will change actually more or less everywhere, every place. So it looks like we won't be able to exploit any kind of, I mean, it looks like making even one small change here leads to huge amount of change in the last table. And maybe that's it. Maybe it's better to just solve from scratch or something like this. So here we'll employ a little bit of a trick. We'll do it as follows. So, well, let's consider an example, and then we'll summarize what happens in general. So the question will be what if coefficients of x3 in expression for z change So now my change in this problem is here. This 8 gets updated to a 10, this 3 gets updated to a 4. So the change is still localized on column, but now changing these two numbers will be reflected. Well, this 3 will be updated to a 4. Here something will change. The determinant of this matrix will change. For example, this number will change. So basically, this whole matrix will change. This vector will change from 3,8 it will become 3,10. So probably the shadow prices will change, which is CDP inverse. Everything will change. Okay, so if you try to find the solution where x1 and x3 are basic, well, you'll have to update everything. It's usually lots of calculations, not the best idea. So what we'll do is, we'll find the table but not quite the table where x1 and x3 are basic. That will be somewhat hard. You'll find the table where we start with the original table and perform exactly the same sequence of operations in the simplex algorithm that we used in the first place. So if in the original simplex algorithm, in the first step we add 3 times the first row, or let's say subtract 3 times, add 3 times the first row to the second one, here we'll do exactly the same. So basically, regardless of what variables are basic, non-basic, we'll just repeat exactly the same steps. What does it amount to? Well, it amounts to basically taking this thing and using the same matrix B inverse to go from here to here. So we'll find the table that we get from the original one, from the new original one, by doing the same operations on the rows. I use the same B, the inverse, and C. So we'll treat, yes, this change is in a column for a non-basic, for a basic variable, but we'll treat it as if it was non-basic. So we'll disregard the change in B, change in the inverse, and change in CV. We'll just update what happens, what is the change in the column of X3. So let's see how it works. My new code for X3 is 10. My new column of X3 is used to be 5.3, now it's 5.4. I'll use the same B inverse to update. B inverse times 10 plus 3 is 3 minus 5 minus 1, 2. Plus 5, 4. So it will be 15 minus 2 is minus 5. Minus 5 plus 8, 3. New coefficient will be CX3 minus CVP inverse. Minus 3. So it will be 10 minus 1, 1 times 5, 4. So it's 1. So new table. I'll copy this one, except this change in this column. 1, 0, 0, minus 1, 1, minus 1, 0, oops, sorry, minus 5, 3, 1, and then it continues. 3 minus 1, minus 1, minus 5, 2, minus 1, 2, 1, 0, minus 14. So I updated my table as if the change was in a non-basic variable, as if X3 was a non-basic variable, as if the change in these numbers did not have any influence on the inverse, on B, on CV. Well, that's not true. And now I have to pay for this. This table is not a basic table. So because I took a basic variable, I updated it in the wrong way, as if it used to be, as if it is non-basic, and now I don't have it. I don't have the basic variable. This column wants to be 0, 1, 0, but now it is minus 5, 3, 1. So, of course, the variables which used to be basic, except X3, are still basic. Still I have 1, 0, 0 for X1, but this one is not basic. I do want to make it basic. How should I do it? Well, just do pivot. I mean, this is a solution. Yes, it is not basic. Let's do some pivot to make it basic. I want this thing to be 0, 1, 0. Let me make the pivot right here. Now, perform a pivot to make X3 basic once again. So this change from the original table to the table updated only at one column is very fast. You just update one column. This change, a pivot, will be a little slower, but not that bad. After all, it's just one pivot. So let's do this. Okay, so let's find the coefficients in the last row. Of course, we'll have 1, 0, 0, 1 for X1 and X3. In the last row, we'll have the following. We'll have to subtract 1/3 of the second row from the last row. So So it will be 0, minus 1, minus 1/3, minus 4/3, 0, minus 4/3, 0, minus 1, minus 1/3, minus 2/3, minus 1, minus 2/3, minus 5/3. So minus 2/3, minus 5/3, and z minus, well, not quite 14, 14 and 1/3. And these numbers will be 1/3. And here it will be 2. I'll have to add to the first row 5/3 of the second row. So 2 plus 5/3 times 1, 11/3. And I'll get some numbers here. Sorry, this is a little small. I'll read it aloud. 1, unknown number, 0, unknown number, 11/3, 0, unknown number, 1, star, 1/3, 0, minus 4/3, 0, minus 2/3, minus 5/3, and z minus 14 and 1/3. So, in this table, I do have a basic solution. It is feasible, these numbers are positive, 11/3 and 1/3, and it is optimal, these numbers are negative. Here we are lucky, so a feasible optimal solution. In general, in this case, we will not always be lucky. One obvious thing, we update this whole row, we might get some positive numbers. Well, that's easy to deal with. We just perform the traces of the simplex algorithm. A little more disturbing, we are performing a pivot which does not come from the simplex algorithm. We are making a pivot to make some variable basic, but it's not the simplex algorithm that tells you make it basic. It's just we are performing kind of the same steps of the simplex algorithm which work for a different problem. They don't have to work for our problem. So these coefficients, these updated numbers, do not have to be positive. And that's a little more disturbing, at least for now, because we don't know how to, well, at least for now, we don't know how to go from a non-feasible solution to a feasible solution. We will learn next time. I mean, in a way, we do know one way. We know the two-phase simplex algorithm, introduce some artificial variables, try to minimize the artificial variables and find a feasible solution. We'll talk about slightly different approach next time. But anyway, this way we know how at least to update our final table using not that many calculations. Or at least, I mean, if it were not optimal and not feasible, we would still have to complete the whole table, which is more or less the same thing as finding the new inverse and updating this thing. But maybe it's a little bit nicer to do this way. And this way we can also stop a little bit short of computing everything. So maybe any questions about changing a basic variable? So to summarize what happens to a basic variable. And this will be the last thing for today. And we'll cover changes in right-hand sides next time. So basically we covered all possible changes except for changes in right hand side. Okay, so changing the efficiency of the basic variable. So one, update the final table as if the variable was non-basic. We use the same V inverse and CV. So if you use the same V inverse and same CV V inverse, the change is only in the column of the variable. So let me say changing coefficients of the basic variable xi, of the basic variable. So if you use this kind of procedure, well, the only change which will happen will be localized to the column of this variable. Unfortunately, as we've seen, this variable will cease to be basic. This new column will not be a column of zeros and ones. The updated column will not be a column of zeros and one. So this variable in this updated table will not look like a basic variable. So we have to fix this. So second step is to fix this, perform one pivot with pivot column xi, pivot row xi. So I mean, the pivot row is the row which originally had zero, which originally had the one as a coefficient for xi. So here we have, why did we choose the second row as a pivot row for this variable? Well, I wanted to make this place 1. So this, so here the basic variables are x1 and x3. So here the pivot would be on the row of x3. In general, it will be on the row of xi. So let me explain it a little better. The row where xi should have coefficient 1. Once you make this pivot, you'll get a new basic solution. Unfortunately, it's not going to be always feasible nor optimal. So the new solution, new basic solution will not in general be feasible if right hand side once you update, once you make this variable basic, you're not guaranteed to get a feasible solution nor an optimal one. But still, somehow it should be not that far away from the optimal feasible solution, from the actual answer. So what you do is, if it's feasible but non-optimal, make several iterations of the simplex algorithm. If it is non-feasible, well, so leave it in the air. We'll talk about it next time. You continue. See you next time. And please take the cookies.